Hi everyone, my name is Zijian Wang. I'm a PhD student from Technium, Israel Institute of Technology. My supervisor is Professor Raphael Sachs. Today I'm going to talk about graph representation of building information models. This is a lovely house. If you want to design such a house, what tools would you use for design? And how can you store the drawings? This brick may give us some hints. This brick actually was created around 3,500 years ago in ancient Egypt. Currently, it's collected by the Metropolitan Museum of Art in New York. This brick contains the architecture drawing of a garden. As you can see, the upper part, the red lines, is part of the temple, and the black solid line is a wall. The notation we should read from right to left hand side. The semicircle stands for 10 and the straight line stands for 1. In total, it means 32 cubits. This brick is so important. It actually reveals one of the most important design tools in history, which is hand drawing. The design theory behind hand drawing is 2D drafting. Architects need to project a 3D object into 2D plane and use lines and annotations to represent the idea. And then the drawings are stored on walls, stones, and later papers. All of them provide a 2D plane. With the development of computers, computer-aided design, CAD, appears. The first CAD software was Sketchpad was invented in 1963 at MIT. Back that moment, the computer mouse has not been invented yet. Therefore, the researcher used a light pen to mimic the physics pen. You need to draw the start point and the end point. Then the computer can generate the line segment directly. This still using 2D drafting as a design theory. It still uses lines and annotations to represent the data. However, it starts to use digital files to store your drawings instead of papers, which is much more convenient. This is Lizi Soho in Beijing, China. It's designed by Zaha Hadid. As you can see, she used a lot of really complicated curves which extend inside and outside. Actually, this building is also multifunctional. The underground is a metro station, and the ground are two office buildings that are putting together. It actually puts a really challenging structure analysis for ensure the safety of both the underground metro and the above two buildings. All of them require the architects and the engineers to design in a 3D manner. The technology behind Lizi Soho is building information modeling, BIM. Instead of using 2D drafting, BIM start to use 3D modeling as a design theory, which can save the process of projecting one object from 3D to 2D and the reconstruction from 2D to 3D. Additionally, it starts to use objects and relationships to present data. For example, a cube is not only a collection of lines anymore. It also stands for a wall in BIM. However, BIM still uses digital files to store media. This is not changed. It seems that BIM can help users to encapsulate their ideas and describe their work very accurately within one domain. However, BIM is not so adapted to the federated AEC industry. The architecture, engineering, and the construction industry is so fragmented. One construction project may involve many experts from different backgrounds, such as architects, engineers, constructors, so on and so on. And all of them prefer to use their own single domain-specific model instead of using a holistic one, that will result in multiple sources of data, even for one project. Additionally, those models are created from different software, and those software may set limitations between them for data exchange, meaning that the model created from software A may not be accessible for software B. Therefore, the industry proposed the IFC schema as an open, vendor-neutral schema to mapping information from BIM software into the IFC files for data exchange. A typical design workflow involving different experts and software could be like this. It starts at the architecture. The architecture exports the architectural model into architectural IFC files and deliver the IFC files to engineers. Structural engineers and the MEP engineers start to work in parallel. After that, they also export their models into files, and then they input all their models into Solidbrief for clash detection. They find out clashes, which will guide them to improve their work. One run and another one, and they need to manipulate and operate and control the versions of the files. At the end, they are confused where they are. As you can see, this is a file-based exchange resulting in sequential design. Users need to manually check and resolve conflicts, and the system has no functionality to help them automatically identify and resolve. Additionally, users need to manually control the versions. It's really cumbersome. When we look outside of the AEC industry, it seems that the cloud collaboration is almost everywhere. One example comes from Microsoft Word 365. You can just share a link of the document to your colleagues. Then everyone can access the same file from different places, from different devices. Everyone can create and edit together. Similarly, in our neighborhood, the manufacturing industry also has Onshape. It can allow different users to access the same model and show the modification in real time. However, there is some difference of the cloud collaboration between their models, their industry, and our industry. The most obvious one is that they rely on the single software, such as Word or Onshape. However, we have so many different types of BIM software from so many different backgrounds and domains. Additionally, they rely on single source truth data while we generate heterogeneous data. So how can we enable BIM cloud collaboration? The industry may give us some solutions. For example, the Autodesk BIM Collaborate allows you to upload files from local Revit software to the cloud, and it can help you record the design changes in files. And you can manually select different files, then compute their clashes between them. However, the software or the platform cannot help you automatically identify and resolve all those changes across domains. And they cannot help you process the design versions at the object level, meaning that sometimes even you just modify one parameter of the wall, you need to sell the whole model. Like the size of the model could be more than 1 gigabyte sometimes. And this platform is mainly designed for Autodesk ecosystem. If you use other software, maybe you cannot use this solution. We also have some similar platforms, but all of them seems like they just simply place the files from local to the cloud, and they cannot really enable a cross-domain intelligent application and collaboration. There is also a startup company called Speckle, which provides an object-based solution. What it actually do is to provide connectors for various design tools. Those tools can retrieve information from the local software and send it to the cloud. Also receive information from cloud and write into the local software. and it can compute changes at the object level, but it cannot still help you identify or resolve all those changes and conflicts automatically. Even though it can compute the change at the object level, but it still saves the whole model, which is not really efficient to my understanding. And there is no semantic enrichment process inside, meaning that when you communicate from the local software to the cloud server, there is a mapping process. It requires you to manually confer the mapping or set your own rules. So they cannot process the mapping automatically by some semantic enrichment algorithms. For example, if there is some object which is beyond the scopes and the rules they already presetted, which means that you need to set your own rules trying to map this object to their respective cloud server. Even though they regard data as objects, but they barely use the advantages of objects, and they also lack intelligent functions to support multidisciplinary collaboration. In the academia, researchers have started to explore Bing graph applications, many within one single domain. Graphs, from the perspective of mathematics, consist of nodes and edges. Each edge associates two nodes. Researchers point out that graphs have the natural advantage of representing relationships explicitly. An early study in our domain is going to compile the layout of one apartment, building layouts into graphs and apply graph searching algorithms to figure out the shortest path as an emergency exit route. Later, Sebastian from Technical University of Munich compiles Bing models as graphs and then compute the design changes and merge the design changes, which achieve the functionality of object-level version control. Machine learning is also applied to Bing graphs. For example, Fiona from Tomb compiles object geometries into graphs. Those graphs come from geometry meshes and applies graph neural network to classify the type of the geometry, such as door, window, so on and so on. Autodesk also adopts GraphGAN to generate the house layouts. Tanya has tried to use graph neural network for code compliance checking. The linked building data community has explored storing building information in web-based graphs and linking the Bing graphs with heterogeneous data, such as the sensor data. They bring a lot of technologies from semantic web domain, such as RDF and Sparkle, trying to compile, link, and store data. Additionally, they also constructed a series of ontologies which encapsulate the common understanding from users and provide uniform vocabularies and formats to compile the graph. After adopting the semantic web technologies and the developed ontologies, they also constructed a series of converters. For example, they developed IFC to LBD converter, which can help users to compile Bing models from IFC files to LBD graphs. However, during this process, some information such as object attributes and geometries are missed. This is caused those information may not be really useful for their use scenario, and the developers didn't find a really good way to save and store those information efficiently. Therefore, the LBD graph come from IFC files is not really complete. It seems that the LBD community application scope is mainly limited to integrating and retrieving data, and how to link Bing graphs to enable more intelligent applications has not been fully explored by them. Actually, this topic has been studied by some researchers but they didn't validate this concept. For example, in 2013, Thomas points out that we can link two graphs together, two beam models together to achieve the functionality such as cross-model information access and change management. Later, Peter Powers points out that we can link different beam software together. This might be the solution for interoperability issues. Later, researchers use equivalent to relationships to link heterogeneous data to support the decision-making in highway asset management. But this is only limited to maintenance stage. Generally, we found that the theory and the framework of graph representation to support or cross-domain intelligent applications are still missing, and there is no formal validation of the graph-based concept. We understand if we simply place the files on the cloud, it's really hard to enable the beam or cross-domain multidisciplinary collaboration. Therefore, we are going to compile those beam files as subgraphs and use AI techniques to link those isolated beam graphs together, form the linked graph. Then we are going to apply intelligent functions on the linked graph, such as we can track the design change from one domain and propagate to another affected domain. This is my research, graph representation of building information models. My research mainly aims to explore and validate a graph-based approach of representing and linking beam models for enabling a cross-domain collaboration. During this process, we meet the interoperability problem. Therefore, we propose another experiment. They are using generic semantic enrichment to reconstruct a beam graph from pure geometry directly and explore graph neural networks on beam graphs. Next, I will introduce these three experiments, and then we are going to discussion and conclusion. Let's move to the experiment 1, graph-based consistency maintenance. Users design their models in local softwares. Then we use the C-beam connector to retrieve the information from the local software and send it to the cloud server. Then the cloud server compile the information into a subgraph. We do the same thing for all the disciplines. Later, we use semantic enrichment algorithms to link those isolated graphs together and form the CB metagraph dataset. Those relationships could be topology, which describe the facts of two objects in 3D space, and it could be functional semantics and design intent and constraints. For example, there is an architecture wall and a structure wall. Between them, we put the C-beam corresponds to relationship, which is a functional semantic. Additionally, there is an MEP radiator and the architecture wall. We put the MED radiator C-beam attached architecture wall. This is actually a design intent because we are putting the radiator on purpose to attach the wall. And those design intent can be further extended to constraints. We may hope the radiator to be moved with the wall together if the architect decides to relocate the wall. Back to this architecture. So after we got the linked graphs, we are going to place the consistency maintenance mechanism on top of it, which will receive the change, analyze the change, and maintain the inconsistency. In short, the concept contains three main ideas: graph representation, graph linking, and the graph application. We call it C-beam. We use a C-beam prototype to validate the idea. In the developed CBIM prototype, it contains one architecture model and a structure model. They are placed in two different software, and then we construct the CBIM Rabbit connector to communicate with the local software and the cloud. This connector is compiled by Dynamo and Python. It mainly will retrieve the information, communicate with the cloud. And for the CBIM server, it's compiled by Python and some third-party libraries. It contains the graph-based database. It can communicate with the local software. It contains the semantic enrichment algorithms to instantiate the relationships. It also has the consistency maintenance mechanism to resolve all those inconsistencies. Let's take a look at the graph. This is a structure model. We are compiling it into the structure subgraph. We do the same thing for the architecture model. Then we are going to link those two subgraphs to form the CBIM metagraph. Let's take a look at the constraint. For example, the green constraint stands for CBIM bounding box structure constraint between the structure slab 1 and the architecture slab 1. It's placed in the Z dimension, and it requires the architecture slab 1 to contain the structure slab 1. And now this constraint is satisfied. Another one is CBIM exact geometry special constraint between the same two objects. It requires the architecture slab 1 whose geometry should contain the structure slab 1's geometry in XY dimension, and now it's true. So after we got the linked graph, after we place the consistency maintenance, what will happen if architects decide to change their model? This is example. The architects move one wall to enlarge the room. After complete the modification, the architect uploads the latest version of the model into the cloud. The CBIM server receives the change and start to compute whether this change violates any established constraints. If it's violated, then they start to compute propagation commands, trying to resolve them automatically. After that, the CBIM server sends the commands to the local software. Later, the local software receives the commands from the CBIM server. Then the CBIM connector pops out a window, asking the permission from users whether the CBIM server can relocate those objects automatically. If yes, then it will be relocated by CBIM connector, sorry. And then CBIM server also provides geometry reference to assist the design if the change or the inconsistency is beyond the scope of automatic maintenance. Summary of experiment 1. Here, we propose a graph-based theory of consistency maintenance. It contains the CBIM concept, which has three steps: graph representation, graph linking, and graph application. It's necessary to point out that those three steps are not necessary to be linear forward. Everyone can be iterative. And we also propose some CBIM constraint relationships and the maintenance mechanism. Additionally, we developed a CBIM prototype. It involves two software and the local server, and it can resolve the transaction change automatically and provides geometry reference for other types of changes. Let's move to experiment 2. During this process, we realized that the CBIM platform requires complete and correct building information from local software. And however, those data could be incomplete. And those provided data from local software could also have some errors. Therefore, we want to check and ensure the data quality and reduce the reliance on local software. In a more general motivation of the interoperability, in the file-based approach, when users export the model from local software into IFC files, some information is lost. This could be because data schemas are not matched or vendors don't share all the information with you. Therefore, we propose How about we use only the object geometry as input and design a series of semantic enrichment process to predict different types of semantics, and then organize those predictive beam semantics into a beam knowledge graph. Why object geometry? Because this is the fundamental data of 3D design, and tools support export of solid objects into accessible and generic file formats, such as mesh PLY files. And we already know that graphs are really flexible to represent different types of information, especially for relationships. And we know that graphs can enable intelligent applications as demonstrated in previous example. Therefore, we propose the framework of generic semantic enrichment. It contains 4 fundamental semantic enrichment tasks under the context of graphs. They are object classification, attribute computation, relationship determination, and object generation. We also propose a process control mechanism which can execute the design tools in a sequence and organize the results into a graph-based CDE. We select the residential apartment to validate this concept. So after export the geometry, the first step, we use machine learning to predict the objects of geometries, and the results are organized in the graph as nodes. And then we will attach the prediction results to the nodes as a label. The second step, we do attribute computation. We compute 9 different types of attributes and attach and insert under each of corresponding node. Then we do relationship determination. We are going to instantiate the hosting and adjacent relationship between objects within one domain. Later, we do 2 different object generation. The first object generation, we are going to generate the building topology from site to building to floors. The second object generation, we do space generation. We use walls and floors to generate the abstract space. Lastly, we do attribute computation again. We are going to compute the new generated objects attributes. Take a closer look of those tools. For object classification, we'll adopt machine learning algorithms. We constructed a data set which contains 8 different objects in the architecture and MEP domain, And then we are going to apply different machine learning algorithms on the data set. It shows that the random forest owns the best performance, achieved the accuracy of 99%. The second tool is machine learning, is rule-based relationship determination. We are going to use geometry, purely object geometry, to calculate the adjacent to and the hosted relationship. The performance of the algorithm is great. Its accuracy achieves 99%, and its F1 is also close to 1. And it uses 1.8 seconds to generate one piece of relationship. Lastly, we do attribute computation. Here, the input is geometry and object types. The output could be 9 different attributes. For example, we evaluate the delta x, and then it could be the length of the window. Same for the delta y and delta z. We show 2 examples of how to use the generic semantic enrichment. The first application is going to enrich pure geometry model into beam model. For example, you design a pure geometry model in SketchUp. You export the geometry out and use the developed tools to predict different types of different type of semantics and organize into a graph-based CDE. Later, we have another reconstructor to read the information from the graph and going to use the API from Revit to reconstruct the object inside Revit environment. During this approach, we'll achieve the function of enriching pure geometry model into beam models. The second application is that we are going to we are going to enhance BIM interoperability. What we did is that you design in BIM software 1, export the geometry, and then we use semantic enrichment to construct the graph-based CPE, and use the reconstructor to read and reconstruct in the second software. We test this on ArchiCAD to Revit 2023, it works. We also tested between Revit 2023 to Revit 2022, it also works. After manually checking, we found that the objects and attributes are consistent with each other. Summary of experiment 2. Here, we propose a framework of generic semantic enrichment. It contains the 4 fundamental semantic enrichment tasks under the context of graphs. We also propose a process control mechanism to execute semantic enrichment tools in sequence for enrichment. And we show 2 applications of using the generic semantic enrichment for enriching purely geometry model into BIM models, or bridge to BIM software for enhancing the interoperability. Let's move to experiment 3. During the experiment or the current software, they can generate the space objects directly. However, it still requires users to manually label the type of the space. Additionally, we already use graphs to store the building information, and GNN, graph neural networks, one technology from computer science deep learning domain, already show great performance when processing some complicated tasks. For example, trying to classify the types of protein in biology, or trying to recommend the possible friends in Facebook, something like that. So we are wondering whether we can apply GNNs to BIM graphs. If we can, what's the performance? What we did first, we constructed a novel BIM dataset. It contains 224 apartment layouts from 3 different countries. We manually label them in a self-designed matrix and convert the matrix into graphs, and also compute their features. And later, we improved a GNN algorithm. In computer science node classification task, their dataset, their application scenario, the age usually contains very few information. However, age in BIM graphs is really meaningful. They could be different types of topology. Therefore, we want to use the features of the age in BIM graphs, but current GNN algorithms cannot leverage age features. What we did is going to modify the aggregator function, trying to let it to leverage both node and age features, because we believe that this will achieve better performance. And we named the new algorithm as CHE. So we divide 80% for training of the dataset for training and validation, and the last 20% for validation. It shows that our CHE algorithm owns the best performance. Its accuracy is 79%, which is higher than others. It also has better F1 than others. When we go to the confusion matrix, the CHE for each class also has higher accuracy. It shows that CHE has more accurate and balanced prediction ability compared with the state of the art. Summary of experiment 3. Here, we propose a novel research approach that compiles BIM models as graphs and applies GNNs to BIM graphs for semantic enrichment. We also constructed a BIM graph dataset, RoomSage, and we also developed a graph neural network algorithm to leverage age features. Summary of the whole study. The background is that the AEC industry is so federated. Currently, it adopts the file-based approach to exchange their design, which results in a lot of problems. And the whole industry desires a closer and more interoperable collaboration across disciplines and platforms. In my research, we proposed a graph-based approach to represent and link building information for supporting intelligent applications. We developed a CP prototype to validate the concept, the graph concept of BIM models. We also design a generic semantic enrichment framework to enhance BIM semantics and improve interoperability. Lastly, we explored GNNs on BIM graphs to leverage topologies of graphs for semantic enrichment. Compared with the state of the art, the first work compared with the commercial cloud software will illustrate the functionality of maintaining design conflicts on linked BIM graphs rather than files. It can facilitate coordination among participants and provide suggestions to improve designs. It's more collaborative, efficient, and intelligent. Compare our work with the existing studies. We propose the framework and architecture of the CBIM platform. We also developed a CBIM prototype to validate the concept. For semantic enrichment works, we define the fundamental tasks of graph semantic enrichment and illustrate the feasibility of accomplish those tasks by constructing AI tools. We also present a novel approach to address the interoperability challenge by employing purely object geometries. And we construct a BIM graph dataset and an algorithm which are open for public use. Limitations. This study faces a lot of limitations. Maybe the first one could be that we only explored one possibility, one possible intelligent applications on the linked graphs, which is cross-domain consistent maintenance. Additionally, the CBIM prototype can only resolve the transaction conflicts. Other than that, it can only offer geometry reference. We think expanding the scope of automatic maintenance is very important for the future. And the CBIM prototype only develops one plugin for one software and one local server. For semantic enrichment task, all the tools we develop are limited to the residential apartment scenario. There is a need to develop the tools for wider scenarios, like can be applied to roads, to bridges, and so on and so on. Even though those tools show great performance in the laboratory conditions, we still think like it's necessary to improve its robustness so it can ensure it achieves better performance when it meets some real world new data. Additionally, currently the graph neural network experiment, the graph generation process is manually, and during the GNN experiment, we only use the topology features. More features should be used, and the better performance is expected. Maybe the most important lesson we learned from all those experiments is linking BIM graphs with design intent constraints enables intelligent BIM applications. This is so important. It actually can help researchers to think about another way of using graph information for designing some their desired functionalities. Moreover, generic semantic enrichment can resolve the interoperability issue, and graph neural networks can be applied to BIM graphs for enriching semantics. We also learned something from graphs. Graphs are suitable to host and integrate object-based heterogeneous built environment data. It can represent BIM object relationship explicitly. Additionally, graphs can enable graph learning for both generating new semantics and supporting intelligent applications. Future works. For industry, we think those following two topics will be interesting. One is trying to develop more CBIM plugins for common BIM design tools such as Revit, Tekla, so on. And we think the CBIM server should be placed in commercial cloud graph platform instead of local server. For researchers, maybe the most important research for the future is to investigate the potential of designing the CB methodology to encapsulate design intent and constraint relationships of objects for both within and cross-domain. It means that we should summarize the understanding from users about design intent constraints of BIM objects into ontologies, provide the design intent classes for software. The second important research topic for the future is to examine the feasibility and performance of using graph learning to generate multi-class or cross-domain relationships. The first topic is going to provide the design intent ontology, which is at the class level. Therefore, we should use some learning-based algorithm to instantiate those classes for some instance models, trying to link them together. It's necessary to point out that those tasks generating multi-class or cross-domain relationships is a very challenging task. Even in the computer science domain, they have a few study about this. Moreover, we think studying learning-based algorithms to propose solutions for resolving conflicts automatically is also meaningful. And we should expand the scope and the scenario of generic semantic enrichment tools and to develop more accurate and robust methods as well as tools. Lastly, we should explore more intelligent applications on the linked BIM graphs. For example, maybe we can integrate the large natural language processing model with the linked graph. Users can communicate with it, and the machine can understand the user requirements and execute the actions automatically. Conclusion. It's a really long history of design tools. We come from hand drawing to CAD. Now we are using BIM. My research is not going to challenge the design theory of 3D modeling. However, I'm going to use linked graphs to represent data. The linked graphs contain single or cross-domain relationships. And we are going to use cloud database to store the data instead of digital files. We call it CBIM. Even though this research shows some good results from the experiments, it's necessary to point out that this is an exploratory study. We are going to validate the feasibility and the possibility of the graph-based approach. We are not going to provide a perfect solution or a product that you can use immediately. We understand there is a really long journey waiting for us. We hope one or more researchers and the industry could join us together, explore those meaningful and unknown topics. The only thing we know that this is the start of the beginning. Thank you very much. This is the publication records in the past 3 years during my PhD. As the main author, I published 4 journal papers, 4 conference papers, and we have submitted 1 patent to the US, which is under review now. And this research is part of the cloud-based building information modeling project. We received funding from European Union's Horizon 2020 Research and Innovation Program under the Marie Curie grant. Thank you very much for your listening.